Hello! So in the previous video we have learned how to train a neural network. Unfortunately, we had to use the algorithm that was very slow and inefficient, and it wasn't very smart about understanding the amount by which we need to change our weights. As a result, we had several problems that I have promised you we will resolve by using a smarter and much superior algorithm. In this video, we are going to learn about this algorithm. It's going to be very cool, it's going to be very powerful, and it's going to be the algorithm that is actually used in real-world neural networks, and we will be able to use it to train our neural networks much faster and make them much more precise. But before we understand this algorithm, we will need to understand something called a derivative. By understanding the properties of this mathematical method called derivative, we will be able to understand how it can be used in order to achieve the results that we want. So what is a derivative? Well, if you have a function or perhaps a mathematical equation that contains two variables and describes the relationship between them, you can use the derivative to understand the direction and amount that one variable changes the other. You use it to understand the relationships between them, and that allows you to do the kind of learning that we want to accomplish. So for example, if we would have an equation that describes the relationship between the error and the weight, we would be able to use the derivative to understand by how much we need to tweak the weight to reduce the error. So first of all, what do we already know about the error? And would we be able to use this information to come up with some sort of an equation that describes the error in terms of weight? Well, let's see. How did we calculate the error in the past? We have calculated a prediction using our neural network, which multiplied the inputs by the weights. And then we have compared this prediction to the target prediction that we wanted to achieve, and we squared it to calculate our square error. So as you can see, prediction depends on inputs and weights, and it is also used in this equation. So you would be able to replace this variable by inputs multiplied by weights. That way we will have one big equation that calculates the error, like so. So we will simply put the calculation of prediction inside of this error equation. And this part is very important to understand. All this does is calculate the prediction of a neural network and compare it to the target prediction, the one that we needed to accomplish. So look at these variables. Actually, if you think about it, only two of these are the ones that are subject to change. So by changing the weights, we will change the error. However, we will not be able to change the inputs and target prediction, because both of those are given us by data. Data gives us the measurements that we will use to make a prediction, and they are pretty much set in stone for every example, and the target prediction is the output that we are trying to achieve, and it's already set by the data and it's given to us. So the only two variables in the actual mathematical sense here are the error and the weight. So this is the equation that describes the error in terms of weight. And it turns out that this is exactly the kind of the equation we will be able to apply derivatives to in order to understand how to change the error by tweaking the weight. So now I want to draw a little plot to help you understand what derivative is and what it actually does. We will not go too deeply into understanding the math behind calculating derivatives, because it's not the subject of this course and it's not really necessary in order to understand the deep learning. What matters is understanding the properties of derivatives and the way they allow us to achieve the learning that we want. So the first thing that we want to do is to plot errors and weights on one graph and see how they relate to each other. What is the relationship between these variables, how they impact each other. So I will just copy paste a batch of code so you don't have to watch me type. It's a lot of code, but I will take you through it and it will be pretty clear what's going on. So this is the graph that we have created. We have weights on the x-axis and errors on the y-axis, and each represents how error depends on the weight. As you can see, as we are increasing the weight, the error keeps going down, down and down, just exactly as we want. But then at some point, we reach our optimal weight that takes the error down to 0. So here around the weight of 3.5, the error reaches 0, and that means this is the optimal weight that achieves our perfect target prediction. And as we keep increasing the weight after this point, making it larger and larger, our predictions begin to overshoot the target, and they become a bit too high compared to what we want, and the error keeps increasing as the error drives the prediction upward, way beyond what it was supposed to be. So let's look at the code and understand what it does. First, I import a couple of libraries. NumPy allows me to create a range of numbers, and matplotlib allows me to draw such plots. We defined our inputs and target prediction just as before. These two variables would come from the data, but instead of weight, as I used to, I define weight range. That is, instead of just using one weight, we are using a set of weights between -6 and 14. These numbers are just randomly picked to create a pretty graph. What matters is that there's a bunch of weights that we are going to try out and calculate the error for each of them. So I have a function here, calculate error, and it does exactly what we did always. So it calculates the prediction, it puts it here, and uses our equation to calculate our error. And then I create a function that plots our weights and errors. I set labels for two axes, and then I pass it the range of the weights for the x-axis, and then for each corresponding y value, I calculate the error for each weight. So for example, at minus 5.0, the error is going to be around 3.5. And for each of these points, I calculate the error to draw the graph and see how it looks. So important thing to understand about this graph is that it shows us how the error changes with the weight. As the weight gets closer to the ideal value of our prediction, the error keeps decreasing. But then as gets farther away from it, it increases again. This lowest point in this graph is exactly what we want to find, because this is the one where the weight is optimal, because it drives the error down to zero and therefore results in perfect predictions. So let's see how we can use derivative to accomplish this, because that's what exactly we are going to use it for. Usually, derivative simply means a slope of a function at a certain point. It describes how steep the curve is. So right now I'm going to copy and paste a bunch of code that you don't really have to understand. All it's gonna do is draw a slope at this line, a so-called tangent, at every point that I want to specify, and this will visualize what derivatives actually are and what they allow us to accomplish. So here's a bunch of code. You can always look through it, and it's pretty well commented out, but don't worry about it, it's not the point of this video. The important thing to understand is that we can now use this function to draw the tangent at any point of our function, like so. So first I will again plot the errors. I will draw this graph at this line of code, and then I will specify the weight at which I want to draw the tangent line, and I will use a function that draws it onto our graph. So this is the result. We again have the relationship between the error and the weight described by the parabola, and then we have a tangent line at point of minus 2.5, which is just a random weight that I have picked to demonstrate to you how it looks like. You can see this line represents the tangent, and in other words, this is a slope of a line, and in yet another words, it's a derivative. So this is exactly what a derivative represents, the incline of this line. Let's try to experiment with multiple weights to see how this line behaves and what we can learn from it. I will go ahead and use the same function to draw a whole bunch of tangent lines at several points on our curve. So there are several very important things to notice about this image and understand about what's going on with derivatives. First of all, you can see that the slope kind of points towards the optimal weight. Actually, we will learn that it points in the opposite direction in a certain sense, but the important thing is that you can see the slope is kind of inclined towards the weight. So if you imagine dropping a ball somewhere over here, it would slide down right down to the optimal weight that we want by following these lines. The second and maybe the most useful thing to notice is that to the left of the optimal weight, the slope of the derivative is negative. As you can see at the weight minus 3, the slope is minus 0.52. Then at 1 over here, the slope is minus 0.2. And at the perfect weight, the slope is 0. And as the weight keeps increasing and overshooting our target prediction, the slope keeps increasing, and at this time it's already positive. This is very important because this will allow us to understand in which direction we want to move the weight in order to minimize our error. So another way to put it is that slope always points in the opposite direction from which we want to modify our weight. For example, let's say at point minus 3, where the weight is minus 3, and our perfect weight is 3.5, what do we want to do with the weight? We want to increase it. We want to go from minus 3 to a higher number to get closer to 3.5. So when we want to increase the weight to improve our predictions, the slope is negative. So at point 1, the slope is still negative, and that means we want to add something to the weight in order to improve the prediction. But then when the slope is positive, so for example at point 10.0 over here, in order to move towards our optimal weight over here, we actually want to subtract something from this value. So that means that whenever we want to move towards the perfect weight, we need to use the opposite side of our derivative, move in the opposite direction from which it's pointing. The third very important thing to understand is that as you move farther and farther from the optimal weight, the derivative gets steeper and steeper. As you can see at the perfect optimal weight, the derivative is 0 and it's completely horizontal. But as you go farther and further away from it, the slope of the line gets steeper. And this is also very important because the steepness of the slope is going to represent the amount by which you want to change the weight. So when we are at the optimal weight, the amount will be 0 because we don't want to move anywhere at all. but we are pretty close to the weight, like for example at point 1, the absolute value of the derivative will be pretty low, and as we get further and further away, the value will keep getting higher and higher. So these properties, they're always pointing towards the optimal weight and getting it steeper and steeper as we get away from it, is what will allow us to use the derivative to find the perfect weight for our neural network. So to recap, why do derivatives matter? They matter because for any function, you can use them to learn how to change one variable so that you can move another variable in the direction that you want. If the derivative is positive, then when you change one variable, the other will move in the same direction. So for example, here to the right of the optimal weight, as the weight keeps increasing, the error is also keeps increasing. So as long as the derivative is positive, the both variables move in the same direction. Increasing weight increases the error. To the left of the optimal weight, as the derivative is negative, the increase in the weight will result in decrease in the error. So as you increase the weight, getting farther and farther to the right, the error will get lower and lower and lower. And the important thing to realize here is that you can use this information to figure out in which direction you need to tweak the weights in order to reduce the error. The slope sign gives us the direction, and the slope steepness gives us the amount. So in the previous video, all we needed to do is to learn how to find the direction and amount in which to tweak our weights, and now we know this exact information. So let's recap everything we have learned so far, not just in this video but overall. A neural network is really just a bunch of weights you can use to compute the error function. And for any error function, you can compute the relationship between any weight and the final error of the network. With this information, you can change each weight in the neural network to reduce the error down to zero, which makes this neural network good at predicting things. Therefore, we are able to use the derivative to create a very cool and very powerful learning algorithm that will drive the prediction of our neural network towards the perfect point that we want to reach. The algorithm that we are going to use is going to be called a gradient descent. All it's going to do is it will use a derivative to start at some random point in this curve, and then it will follow the slopes of this curve. It will follow the derivatives tiny step by tiny step. It will descend towards the lowest point in this curve, which is why it's called gradient descent. It will descend by this curve down to its lowest point, and once it finds its lowest point, our predictions will be perfect because our error will be zero. Excellent. I hope you understand this, and I hope this video was useful to you. And in the future videos, we are going to use this information to write the actual code that is going to train our neural network very quickly and efficiently and allow us to make great predictions.